Okay, so we can start. So I was told by Andre that the big seminar is for famous established speakers. So I thought that Dano is the right person for that. He was Benny Sudakov's PhD student, and then he had a postdoc position, the PFL, and now he is back to England. He's in Oxford, and he's a famous established speaker who doesn't need an introduction. We got to the point, so please start your talk.
Okay, thanks, Janusz, and thanks for the invitation. It's great to be here. So I'll be talking about a new stability theorem for the Turán problem that I worked on with Alex Roberts and Alex Scott from Oxford. And in some sense, we're going to revisit the classics of extremal graph theory. So let me start at the beginning. So extremal graph theory starts with the following question. Given a forbidden subgraph H, how many edges can an H-free graph on n vertices have? So suppose I have an n-vertex graph that does not contain H as a subgraph. What's the maximum number of edges that this graph can have? And in fact, the first questions of this sort were asked for cliques. So what if H is a small complete graph? So this, after some early result by Mantel for the triangle-free case, this was answered by Turán in 1941. So he proved that when H is a clique of size r+1, the number of edges in an H-free graph is maximized by the so-called Turán graph, which really is just a complete r-partite graph with parts of essentially equal size. So you have R parts, R independent sets here of size n over r, floor or ceiling, and any two vertices in different parts are connected by an edge. So Turán proved that this graph has the most edges among graphs that do not contain the clique of size r+1. And in fact, this is the only such graph. It's a unique maximizer. And the number of edges in this graph is roughly r-1 over 2r times n squared. And I'll denote it by T sub r of n. It's the so-called Turán number. Okay, so Turán's theorem says that for when H is a clique, the number of edges is maximized by the Turán graph. But actually, the Turán graph is extremal for, or essentially extremal for every graph that has chromatic number r+1. This is the famous theorem of Erdős, Győri, and Simonovits. So they proved that so if H has chromatic number r+1, then the maximum number of edges in an H-free graph is asymptotically the same as asymptotically the Turán number. Okay, so these are kind of the fundamental theorems of extremal graph theory. And so they answer this problem for all graphs with chromatic number at least 3. Right, if the chromatic number is 2, if H is bipartite, then what happens here is T sub r of n, T sub 1 of n is the number of edges in an independent set. So that's just 0, and this whole thing just collapses to the little o n squared error term, which was supposed to be the error term. Right, so when H is bipartite, then this doesn't give us the asymptotics of the optimum. So I guess one direction of further research here is to determine the maximum number of edges in H3 graphs where H is bipartite. And so that's what last week's talk was about, where David Conlon gave a nice survey of how things stand in this area. So today I want to talk about a different aspect of these theorems, namely that they are stable. So what do I mean by that? So stability in general means something like, we want to say that whenever our object is close to some target in its size, it has roughly the same size as some target, it must have roughly the same structure as well. So in this case, the stability theorem will say that if you have an H3 graph that has roughly the same number of edges as an extremal graph, roughly maximal edges, then it must have roughly the same structure as the Turán graph. And yeah, so I'll shortly specify what I mean by these roughly, but for now, let's just say roughly the same structure means that the graph should look like the Turán graph. It should have R parts of size roughly n over R. Each part is roughly independent, and between any two parts, you get a roughly get a complete bipartite graph. So this is the stability theorem for this extremal problem, and it's a classic result by Erdős and Simonovits from the 1960s. Okay, so of course, stability theorems like this have a lot of applications, and so before I go deeper into this topic and present our results, I wanted to show an application of this stability theorem. And since this is a combinatorics and discrete geometry seminar, I thought I would start with, or I would show an application to a discrete geometry problem, namely the unit distance problem. So the unit distance problem asks the following: suppose you have n points in the Euclidean space of dimension d. How many of these points, how many pairs of these points can have distance 1? So this is a very famous and old question of Erdős. Goes back to 1946. And yeah, if I denote this number by g sub d of n, this maximum number of pairs at distance 1, then so this problem has an answer. So it's known what this g sub d of n is. It should be roughly, again, the Turán number t sub r of n, where r is d over 2. So the dimension, if the dimension is 2r or 2r plus 1, then the maximum number of point pairs at distance 1 should be given by this Turán number. Now, of course, saying that this problem is solved, it might be a little bit of an exaggeration, because again, if r is 1 here, so if the dimension is 2 or 3, then this term vanishes. So we don't get an asymptotic answer for this problem, just that it's literally n squared. And indeed, the most difficult special cases of these problems are the 2-dimensional and 3-dimensional cases, and in those cases, the problem is wide open, and there's active research going on. But I wanted to talk about the higher dimensional case. So I want to prove this theorem. So again, we're on dimension d, where d is 2r or 2r plus 1, and I want to show that the maximum, if I have n points in this space, then the maximum number of point pairs at distance 1 is given by the Turán number. So the proof is fairly short and simple. The lower bound was given by Lentz in 1955, and the construction is as follows. So let's take our circles that are pairwise orthogonal in the d-dimensional space. So D is 2r plus 1, so we can always find pairwise orthogonal circles here, r of them. And yeah, so let's say they all have the radius 1/√2. So this means that any two of these circles have distance 1 in a strong sense, namely any 2 points on these, like any 2 points on different circles will have distance exactly 1. That just come from orthogonality. So to construct the point set, we can just pick any n over r points on each circle, and then so if you look at this unit distance graph of this configuration, of this point configuration, where you connect 2 points if they're distance 1, and you don't connect them otherwise. So you can see that any 2 circles, which will correspond to the parts, any 2 circles are completely connected to each other. So this construction will give you edges, all the edges of the Turán graph. So you get at least d sub r of n edges. And in fact, if you're clever, you can even get more edges within the parts by choosing these n over r points in some specific way, so that they also have unit distances among them. Okay, so this is the lower bound, and for the upper bound, Erdős noticed that if you take any n points in the plane in the d-dimensional space, for these 2r or 2r plus 1, the unit distance graph of this point set will always be k3, 3, 3, 3, where this is the r plus 1 partite graph where each part has size 3. So the unit distance graph will not contain this r plus 1 chromatic graph, which means that you can just apply the Erdős-Simonovits theorem to show that the number of edges, or in other words, the number of unit distances, is at most d sub r plus some error. Okay, so that's the proof of the theorem. We didn't use the stability theorem, so you might ask what was the point? And the point was that if we use the stability theorem, so here we use the Erdős-Simonovits theorem, but if instead, so we use this theorem just to get an upper bound on the number of edges. But if instead we use the stability theorem, we can say more. So in particular, the stability theorem says that this unit distance graph should have roughly the same structure as the Turán graph. In the sense that I haven't really explained. But you can use this fact that it roughly looks like this. You can use this fact to show that most of the points in each part must lie on the same circle. In fact, that was done by Erdős and Balogh in 1990. And using this observation, they managed to pin down what this error term actually is. They found the order of magnitude of this error term for every dimension of this error term. I mean, for every dimension d at least 4. Actually, the even dimensions are a bit simpler. And that was done by Erdős a bit earlier. For odd dimensions, they were the first one to find it using the stability theorem. And you can do even more if you push these methods a little further. So Swainpool showed that if you already know that most points in a part must lie on the same circle, you can kind of bootstrap it into showing that all points should in fact lie on the same circle. And this in fact means that extremal sets, extremal configurations for these endpoint sets should come from this construction of lengths. So this reduces the problem to just maximizing the number of edges within the part. So it boils down to picking these n over r points in the best possible way. Okay. So yeah, so that's how you can apply the stability theorem, and it's a fairly common way of applying stability theorems to kind of show that first you can approximate the extremal graph, and then you can push it further to get exact results. Right. Okay. So that's all the discrete geometry I had for today, I'm afraid. So let's get back to our original problem, which was, so I actually want to talk about how strong the stability theorem is, or how stable how stable Turán's theorem is. But of course, before I can discuss what how stable these theorems are, I should tell you what the stability theorem, what I mean by stability, which I haven't told you yet. Okay, so we need to find a way to measure the stability. And by the way, so our paper is about KR plus 1 free graphs. So it's about the stability of the Turán problem of Turán's theorem. So from now on, I will just work with KR plus 1 free graphs. G will always be a KR plus 1 free graph on M vertices in the rest of this talk. Okay, so Turán's theorem said that this Turán graph maximizes the number of edges in such a G, and then we need to decide what we mean by stability. And yeah, as I said, stability should say something like, if I'm close to the Turán graph, then in its size, or to my target object and its size, then I must be close to it in structure as well. And yeah, so close and size should of course mean that the number of edges in G must be close to the Turán number of edges in this graph. But there are multiple ways to understand what close in structure could mean. So the first kind of classical interpretation of closeness in structure is to just measure the distance of G from the Turán graph itself, meaning how many edges do you need to change, how many do you need to delete or add in G to get to the Turán graph at the end. Another perhaps more modern approach is to look at the distance from just any r-partite graph. So I know that every graph contains an r-partite or r-colorable graph. And so here, my question is, how many edges do we need to delete to get to such a graph? And it makes sense to study both variants. In fact, the Erdős Simonovits stability theorem is equivalent in these two senses. Yeah, so for example, this first version might be a bit more intuitive to measure the distance from the actual extremal graph. Also, it's a stronger statement to say that my graph is close to the Turán graph than to say that it's close to being r-partite. But if we want to go deeper into how stable the results are, then turns out that this first variant is not very stable. For example, if you look at this Turán graph here, and just take a vertex in the first part and move it to the second part. So you get this complete r-partite graph with just one fewer edges than the Turán graph. Then, so its distance in size is just 1. But to get back to the Turán graph itself, you need to modify all these edges. So the distance will be linear. It's roughly 2n over r to the Turán graph itself. So one fewer edges in this graph, and this distance is already linear. That's a pretty big dependence on just one edge. So this first interpretation is not very stable, but if you look at the second, this is still an r-partite graph. And in fact, we'll see that the second version is a lot more stable if you care about if you go very close to the Turán graph. Okay. So right. So another thing is for the second version is that in many of the applications, you don't really care about the structure of the graph. What you care about is that you have an r-partition with very few edges induced by the parts, which is again a motivation for understanding the second version a bit better. And yeah, so that's the version we focused on. So let me introduce some notations. So I'll denote the distance from being r-partite by d sub r of g, and the number of edges by e of g. So our problem is to kind of bound the distance drg when the number of edges is as close to t sub r then, the Turán number. Okay, so that's our problem here. Here's it more specifically. And right, so the fact that Turán, there is stability was established by the Erdős theorem a long time ago. So it just, so here it is in now precisely. So they prove that if the number of edges in my kr plus 1 phi graph is asymptotically the same as the Turán number, then it's enough to delete just a little n squared fraction of the edges to make it r-partite. And of course, the closer we are to being, so the more edges our graph has, the more structure is enforced by this property that the graph is kr plus 1 free. So the closer we will be to being r-partite. But just how close exactly we need to be, that was only studied fairly recently. The first general result of this sort was proved by Furedi in roughly 2006, and then was published a bit later. So he proved that if the number of edges is just t fewer than the Turán number, then it's enough to delete t more edges to make the graph r-partite. And then this result was further refined by my co-authors. Roberts and Scott proved that, improved this bound on t to t to the 3/2 over n when the distance is small enough. And in fact, this bound on drg is of the right order of magnitude. So they proved that among graphs of a given number of edges, on a given number of edges, this upper bound is tied up to a constant, up to a multiplicative constant.
Sorry, then,
and very recently, yeah.
Is delta a constant here?
Delta is a constant here.
So it's not necessarily tied as it's stated for, say, delta equals 1 over n.
Yeah, no, I don't know.
Okay. Okay.
I don't think so.
Okay.
I'm not sure actually. Maybe it is. Anyways, but even this multiplicative constant was determined very recently. And now this result is only for delta equals little o1. So maybe it is tight, I guess. Anyways, so this, yeah, so one might say that this problem is pretty well understood by now. But we can actually say more in certain special cases. For example, if the number of edges is very close to TR of n, then the graph just must be r-partite itself. So the distance must be 0. And exactly how far you need to be, or how close you need to be to the Turán graph for this to happen, well, so that was first studied by Simonovits and later determined exactly by Brouwer. So here, this bound on the number of edges is tight. If you have, there are examples of KR+1 free graphs with one fewer edges that are not r-partite. Okay, so that's an exact result, and we can say even more when R is 2. So the triangle free case is basically solved by this result of Erdős, Győri and Simonovits, which says that among triangle free graphs, and the worst graphs, the ones farthest away from being bipartite, are blobs of pentagons, namely pentagon blobs of this form where you have one part of size x, two of size y, two of size m, and so these shaded areas correspond to complete bipartite graphs. And okay, so this graph is clearly triangle free, and if m here is roughly n over 2, so almost all the vertices are in the right, then its distance from being bipartite is given by these x times y red edges. So if you delete these edges, then obviously you get a bipartite graph, and it's not very difficult to check that. That's the best you can do here, assuming m is large. Okay, so they prove that these are the worst triangle free graphs in terms of distance from being bipartite, which more precisely means that they show that for any triangle free graph with enough edges, there is a pentagon blob that is closer to being closer to the Turán number, closer to the being, yeah, I mean the number of edges is closer to the Turán graph, or in this case the complete balanced bipartite graph, and yet its distance from being bipartite is bigger. Okay, and yeah, so this is the result that we managed to generalize to all R. So what will be the worst graphs in general? Well, okay, so here is the pentagon blob. That's the example for R equals 2. And we can extend this construction pretty much the same way as the Turán graph extends the complete bipartite graph as the example for Turán's theorem. So we just add R minus 2 parts of equal size, x plus y plus n, and connect any two vertices that come from different parts, or rather different rows here. Yeah, in this pentagon, we don't change any induced edges. Okay, so that's a graph we call a pentagonal Turán graph. It's easy to check that it's KR+1 free. And again, the number of, its distance from being r-partite is represented by these x times y edges. All right. So Balogh, Clemen, Lavrov, Lidický and Pfender conjecture that these pentagonal Turán graphs are the worst graphs among KR+1 free graphs. And in the same sense, for every G, there is an H that's a pentagonal Turán graph, which has more edges, so it's closer to the Turán number, but the distance is larger. And our main result is that we managed to prove this conjecture, assuming delta is a small constant. Not super small, but fairly small. Okay, so in the rest of the talk, I want to say something about the proof of this result. And yeah, our proof is fairly technical. It builds on ideas of the Erdős, Győri, Simonovits paper, the r=2 case. So what I plan to do here is first I'll sketch their argument for triangle free graphs, and then explain how we can adapt those ideas and what needs to be changed, and yeah, some comments. Okay. All right, so here's the proof for the r=2 case. So we have a triangle free graph and we want to show that it's close to being bipartite. So what we do is we take a max cut in this graph. So we take a bipartition of the vertices into two sets A and B that maximizes the number of these crossing edges. Okay, so there will most likely be some number of internal edges in this bipartition. But I know that if I delete these internal edges, then I make my graph bipartite. So in particular, if there are T internal edges, then the distance of G from being bipartite is at most T. Okay. So the plan now is to construct a pentagon blow-up in this case.
No, just a small question. So isn't it exactly T, since you took the max cut?
I don't think so. I think, yeah, okay.
So the smallest number of edges you need to delete to get a bipartite graph.
Right. Yes, you're right.
The same as the largest number of edges you keep for.
Yeah, you're right. The reason I wrote this is that I'm cheating here, and we don't actually start with the max cut, and what we're doing will not be equal. But yeah, it's
okay.
In this, yeah, and so for the purposes of this sketch, yeah, it's equal actually.
Okay. Cool.
Right. Thanks. Yeah, and then so the plan is to construct a pentagon blow-up that has the same number of internal edges. So it has the same distance, T. Okay, so you have T red edges here, and that's your pentagon blow-up. And okay, so what we want to prove is that this graph is worse than that. Well, it has the same distance, so we want to prove that it has more edges. It's closer to being the Turán graph in size. Okay, so we want to prove that G has fewer edges than H. Now, since they have the same number of internal edges, it's equivalent to saying that I want to prove that G has fewer crossing edges than H. So basically, I just want to find a good upper bound on the number of crossing edges in G. Let's forget about H for now. We just want to bound the number of crossing edges in this graph G. Now to bound those edges, bound the number of those edges, we're going to use three different arguments, three simple ideas. Right. So yeah, I'll go through them briefly. So for the first one, let's notice that every vertex has more neighbors, more crossing neighbors than internal neighbors. That's because we started with a max cut. So if V has delta internal neighbors, then it must have at least delta crossing neighbors. Otherwise, you could just move V to the other part. Okay. But we also know that the neighborhood of V is empty, right? Any edge here would create a triangle. So in particular, we know that any neighbor of, we know that a neighbor of V cannot send any edges to this set delta, set of size delta here. So the number of crossing edges that it touches is at most B minus delta. It can send edges to any other vertex, but not to this. So that's our first bound. Every internal neighbor of V touches at most B minus delta crossing edges. Okay. The second bound is even simpler. If you look at any internal edge here, we know that the two end vertices of this edge cannot have a common neighbor in B. So every vertex in B can send an edge to at most one of those vertices. So particularly the sum of the degrees, number of edges touching these two vertices is at most B. Okay, that's the second bound. And for the third bound applies to any other vertex in A. And here we can just use the fact that the neighborhood of any vertex is an independent set. So if you have a matching of K internal edges in B, then I know that this vertex cannot send edges to both endpoints of an edge. So if there is a matching of size K here, then the degree of this vertex is at most B minus K. It must miss one end of each of the matching edges. Okay, so these are the three bounds. In fact, they give upper bounds on the degrees of the vertices in A. And so summing those up gives an upper bound on number of crossing edges. And you can notice that the larger this internal matching K, the larger this internal matching was, the better the bound in 3 we got. And similarly, the larger the matching we can find in A, the more we can apply the second bound. So that again, improves our situation. So kind of the larger matching of internal edges we can find in this graph, the better bound we have. And then it turns out that we can find just the right size of a matching here to show that this graph has more crossing edges than that. So that's pretty much the proof of Erdős, Győri, and Simonovits. Okay. So if we want to generalize this proof to larger R, a whole lot of things go wrong. Because, so triangular-free graphs have these nice and strong property that the neighborhood of every vertex is an independent set with no edges in it whatsoever. And there's just no meaningful analog of that for a larger R when you only for a bit larger cleave. Particularly this third bound will not work when R is bigger. But luckily, we can save the first two bounds in some sense and work a bit more to make things work, and that's how we'll get our proof. So let me move on to the ideas of our proof. So perhaps the main lemma that we can use or the main tool in our proof is a really cute lemma, which is essentially just the Turán problem it just solves the Turán problem in complete r-partite graphs. Okay, so let's say L is a complete r-partite graph with parts of size n1, n2, and r. And let's just assume that these are in increasing order. So the question is, how many edges can a KR-free subgraph of this graph have? In other words, how many edges do we need to delete from this graph to make it a KR-free? So one simple way to make it KR-free is to just delete all the edges between two parts. So for example, here, if I delete these n1, n2 edges, then I made my graph KR-free. And yeah, so among deletions of this kind, the best you can do is to delete all the edges between the two smallest parts. So yeah, that's a lower bound on the number of edges, and it's actually the best you can do. So that's what this follicular lemma tells us. It says that every KR-free subgraph of this misses at least n1 times n2 edges. And this has a really nice and simple proof, so let me just do it. It's basically just counting the number of KRs, number of copies there are in this graph. Okay, so let's do that. How many copies of KR is in this graph, or are in this graph? Well, you get a KR by selecting one vertex from each part. And so the number of ways to do that is just n1 times n2 times ... nr. Okay, so there are this many copies of KR in L. Now, let's fix an edge. How many copies of KR contain this edge? Well, again, we need to select one vertex from each part. These two are fixed, but for the other, we can just choose them arbitrarily again. So it will be n2 times nr in this case. And if I assume that n1 and n2 were the two smallest parts, then this number is for sure at most n3 times nr. Okay, so we have this many copies. Every edge is contained in this many of them. So if I want to destroy all the KRs, we need to divide. We need to delete the fraction of many edges here. So in this case, to delete all the copies of KR, we need to delete at least n1 times n2 edges in this graph. And that's exactly what we wanted to prove. Okay. Right. All right. So now we're ready to move on to our proof for general R. And the strategy will be pretty much the same as before. We start with a KR+1 free graph, take a maximum r-partition of the vertices, so an r-partition that maximizes the number of crossing edges. Then again, there will be some number of internal edges, but if we delete those, then we get an r-partite graph. And then we just construct a pentagonal Turán graph with the same number of internal edges And then the want is to prove that the number of edges here, or the number of crossing edges in H, is more than the number of crossing edges in G. Okay, so far it's the same. What's different is, well, there are several different things. Okay, so if you remember in the r=2 case, the way we bounded the number of edges, number of crossing edges, was just to bound the degrees in one of the parts, and that here will not work because bounding the degrees won't just not see all the possible missing edges. So we'll need to be more careful about finding missing edges all over the place. Okay, so let's see what happens with our 3 arguments. Remember, we have 3 arguments for bounding the degrees. The first one was about neighbors of a vertex. So we still know that since we start with a maximum r-partition, every vertex V has more neighbors in every other part than in its own. So if V has delta neighbors here, it must have at least delta neighbors in every other part. And previously we used this to show that this neighbor, like there are many missing edges here because the neighborhood was just empty. Of course, if we only forbid larger cliques, we don't know that the neighborhood must be empty. But we do know that the neighborhood must be KR free, right? Otherwise, we would get a KR plus 1 by just adding V. Okay, so this purple neighborhood is an r-partite graph that's KR free. So by the lemma from the previous slide, we know that at least delta squared of the edges are missing. Okay, so previously we knew that all the edges were missing. Now we only know that we're missing delta squared edges. It's not the same, but it's still pretty good. Okay, so that's how we adapt the first bound. For the second bound was about the common neighborhood of the endpoints of an edge. And yeah, so previously we knew that there is just no common neighbor, and that allowed us to bound the degrees of these vertices. Now again, it's not true that there are no common neighbors here. In fact, these 2 vertices can have a lot of common neighbors. But what is true is the common neighborhood is KR-1 free. So the common neighborhood will form an r-1 partite graph, which is KR-1 free. So again, we can apply the lemma to find the number of missing edges here, assuming that the common neighborhood was large. Otherwise, we can argue that the common neighborhood is small, and then there are many missing edges at these vertices. So here it needs a little balancing. It's less clean than in the first bound or in the previous r=2 case, but you can get something. You can say that, okay, either I have few common neighbors, in which case I'm good, or I have many common neighbors, but then in the common neighborhood there are many missing edges, and that's also good. Okay, so that's how we can save the second bound. And then, so the third bound was to estimate the number of edges touching any other vertex. And as I mentioned before, this cannot be saved. There is just, like, this vertex could, for all I know about it, it could be adjacent to all other vertices. So there is no general upper bound on the degrees. We can't do that. So to see the number of edges missing, at this green vertex, what we do instead is to apply the second bound to other internal edges, not just in the first part, but in the second, and so on. So, yeah, so that's kind of how we go around the third bound. And of course, then there are a lot of issues, because so we're counting the missing edges, and we need to be very careful not to overcount the number of edges. So yeah, there is a lot of technical details that I'm omitting here, but this is well, this is more or less how the proof works. Okay. All right, so I just wanted to show you what the actual theorem gives. So the theorem says that that the worst KR+1 free graphs are of this form, and then to find the actual worst graphs, it's a matter of calculations. You just need to optimize the number of edges. So given the distance, you can maximize the number of edges. And if you do that, or yeah, in this way, I fix the number of edges, and then I want to maximize the distance. And so if you do that, here's what you get. Okay, so it's probably not very illuminating to look at this picture. What I want to emphasize, though, is that this works all the way down or up to the Turán number. So, I mean, not necessarily with these exact numbers, but you can always optimize it. And for example, if delta is 1/n times r, which brings you back to this theorem of Brouwer, where the threshold was for like how many edges you need to be bipartite if you're KR+1 free. Yeah, so this theorem will work all the way up there. And in that case, the construction was actually all these sets will have size 1. Okay. So there is one more detail of the proof. Yeah. Oh, sorry. There's one more detail of the proof that I sort of ignored. Namely, so here to make this proof work, or make this argument work, I sort of need that the degree of V, or there's a vertex with fairly large internal degree, which would, of course, not like just contradict what I just told you, that our theorem works all the way to the Turán number when everything is bipartite, r-partite. So we needed a separate argument when the number of edges is just very close to the Turán number. And it's a pretty cheap argument, and it's certainly not tied to what we were doing, but it was good enough for our purposes. So our main sort of proposition or tool for this regime was to show that when the number of edges is quite close to the Turán number, then there is a vertex that you can delete to make the graph r-partite. So remember, Brouwer's theorem was that if the number of edges is at least t sub rn minus n over r plus 2, then your graph is automatically r-partite. And so we needed to lose a little bit more edges, and but we allow one vertex to be sort of non-r-partite. And yeah, so to prove this proposition, as I said, it's the simplest I could think of. So there is this result by András Fariados and Sós, which says, it's an analogous result to Brouwer's theorem, except it's with minimum degree. So it says that if you have an k r plus 1 free graph G whose minimum degree is bigger than this, then the graph must be r-partite. And so this means that if the minimum degree of my graph is at least that, then I'm already good as far as this proposition is concerned. So I can assume that there is a vertex whose degree is smaller. And then I claim that I can just delete this vertex and get an r-partite graph. And so to see that, you can just do the calculation, and that will give you that if you delete this graph, if you delete this vertex from the graph, then the number of edges will be just a Turán number minus n minus 1 over r plus 2. So I can apply this theorem by Brouwer that I mentioned, and yeah, that will make sure that this graph is r-partite. So that was really simple, and then to prove that in this regime, really the pentagonal Turán graphs are the worst graphs, I just show that if I have a graph of this form, then there is a worse pentagonal Turán graph. So here's what you can do very quickly. So the graph must look like this. You have an r-partite graph here and some extra vertex v, which is connected to some of the parts, or actually all of the parts. And then based on this, we construct the pentagonal Turán graph where, yeah, by the way, so the distance of this graph from being r-partite is just, well, it's at most the number of red edges here. If I assume that A1, A2, A3, A4, the sizes of the neighborhoods are in increasing order, then if I delete these edges, I get an r-partite graph. So the distance of this G from being r-partite is at most A1. And now based on this, I can construct a pentagonal Turán graph whose distance from being r-partite will also be A1. And then I need to show that this has more crossing edges than this. And the way to do that is, again, to appeal to this lemma. So if I apply the lemma to the neighborhood of V, I see that there are at least A1 times A2 edges missing. And yeah, then you can use to bound the number of edges, number of crossing edges here by the number of crossing edges there. So that's a rough sketch of what happens when you're very close to the Turán number. Okay, so that's all I wanted to say about the proof of our theorem. So let me finish with some open problems. Now, of course, the first open problem that comes to mind here is what happens with other forbidden graphs. So can you find exact stability results for if instead of a clique, you forbid some other graph? Now, of course, this is a strictly more difficult problem than the Turán problem itself, which is already can be quite hard. So it's set for bipartite graphs. It's not very well understood at all. But even for non-bipartite graphs, the answer is sometimes not known. The exact extremal graph is sometimes not known. Some other times it's just very ugly. But one class of graphs where the answer is known and it's kind of nice is graphs that are edge critical or edge color critical. So graphs with chromatic number r+1, such that have an edge that you can delete and decrease the number from the chromatic number. So an old result of Simonovits shows that some Turán graph will be extremal for any edge critical graph with chromatic number r+1. So maybe there is some hope to find exact stability results for this class of graphs. In particular, we conjecture that if we take odd cycles, then the exact stability. So if I forbid an odd cycle of length 2k-1, then the exact stability or the worst graphs farthest away from being bipartite should be blow-ups of a cycle of length 2k+1. Okay, so one comment here is, so this conjecture will not hold true all the way to the extremal number. There are some exceptions when the number of edges is very close, but perhaps if you lose at least a quadratic number of edges, or maybe even maybe even very just a little more edges than required by the counterexamples, it could be true. Okay, so that's one question. Another question is, so the stability problem bounds the distance from being bipartite or r-partite in terms of the distance and the number of edges. But it would also be interesting to find just a uniform upper bound on the distance from being r-partite or bipartite among any k+1 free or triangle free graphs. In fact, there is an old conjecture of Erdős for the triangle free case, which says that the worst graph among all triangle free graphs in terms of distance is the blow-up of the pentagon, where each part has size n/5. And so this conjecture is known for if the number, so this conjecture is known if the number of edges is at least n²/5. Well, we know it's the number of edges is at most n²/4. So it's known in that regime. It's trivial if the number of edges is less than n²/50. So actually 2n²/25. So it's trivial in that regime, but in the middle range, it's still very much open. And yeah, so as I mentioned, you can generalize it to larger cliques and larger r-partite graphs. A different way to generalize it is to keep looking at the distance from being bipartite, but forbid larger cliques. And so Sudakov has a conjecture about this, which says that the worst graphs, or the worst graph in terms of distance from being bipartite among k+1 free graphs is the Turán graph itself, when r is at least 3. And again, this conjecture is known for r=3. That was proved by Sudakov, and a proof was announced for the r=5 case, but also all the other cases are open. And yeah, that's all I wanted to say. Thanks for listening.
Thank you, Dano.
So, any questions?
I have a question.
Yes.
First, about this conjecture by Simonovits. So this TR of n, you mean when you're splitting vertices in roughly equal parts, or it can be something else?
Yeah, it's the Turán graph.
Is the Turán graph. Okay. And another thing that I wanted to ask is, you said this, that you don't actually take the max cut for your proof, you take something else. So
Yeah.
maybe you can say something about that. What is that something else?
So, I mean, so I mentioned that for the unit distance problem, I mentioned that it's common that you take a stability result and then kind of bootstrap it to get an exact result, and that's somehow similar to what we're doing. So we actually start with yeah. So we start with a complete. We start with a very large subgraph that's essentially the Turán graph, and then only assign the other vertices so as to maximize the number of edges and the number of crossing edges. So it's more or less the same, except we start with something that's already there, and that comes from like a weaker stability theorem.
Okay, cool. Sorry for people speaking in the background. Someone came to.
Yeah. Any other question? So I wonder, there are all these other geometric applications of Turán's theorem. There is like about distributions of distances. That do you get? So there is something, I don't remember exactly, but you obviously get something if you have a number of points in a region, and you want to know that how many distances, how many pairs can be at distance bigger than a certain number x, right? And then you can apply Turán's theorem, because you see that how many points you can put into the region so that any two of them are at distance x, and then apply Turán's theorem, right? And then maybe you can get something more precise. I don't know. Maybe there it is not known that maybe using stability you can say something that the only way of getting this. I'm not sure if it is true.
But is it asymptotically tight?
Well, it is asymptotically tight, yeah, because you can really, if you can take like 10 points so that any two of them are at distance at least 2, then you just in small neighborhoods of those points, you can take many points. You can repeat them. But maybe you can spread the points a little bit. But maybe you get some kind of interesting geometric consequence just by using stability.
I mean, you're the one who came up with this, not me.
Well, no, but you know, there are infinitely many applications. So I am sure that if there is a stability result, then it's not only the unit distance problem, which where you can kind of apply it.
Right.
And once you put in so much energy.
But I mean, also for Conrad's results, he used the stability theorem to establish the stability theorem. I mean, he used the graph theoretic stability theorem to establish the stability theorem for point sets, and then only worked with the geometry from there on to get the exact result. So I'm not sure you can directly apply these to geometric settings, but yeah, maybe.